Okay, so my screen is visible at all of your ends.
Yes, sir.
Okay, so this was what we were discussing, and yesterday we were discussing about the reflector less as well as with reflector, two different modes of total stations. So reflector less is what we will say is the advanced one, but of course there are again limitations of both reflect with reflector and reflectorless. So initial total station equipment were with reflectors. So with reflectors, it means there was a prism. So a prism was used in the at the observation station. Observation stations, and the total station was focused. The light of beam of the light was made to fall on the reflector, the prism, and then was reverted back, reflected back. Okay, so this was the setup. And recently, some instruments, EDM instruments, they recently means this is approximately 15, 20 years back. People have started, and now that has been more or less standardized. So they don't want reflectors because again installing the reflectors at the observation stations okay, so it should be the observation stations is really the question which was supposed to be solved, and then uh, people wanted to uh, access the data, collect the data about all the possible types of measurements at inaccessible locations also. So the this is one example of a setup which is a laser range finder. Okay, so it uses a laser beam, and then the beam is emanated from the device, also received at the device. So both the transmitter and the receiver TXRX units are installed at the same setup, handheld setup, and uh, based on the electronic circuitry, we can measure the actual distance between the instrument which is handheld with respect to the object where it is focused. So both these were utilized in the okay. So one of your seniors in probably each of the batches, they came up with their own. Now you have a laser pencil which is used. So use that, and then we developed a circuit to receive the signal and also compute the distance. So if some of you want, you can just do that. And what is happening with lasers, it can measure up to a distance of some 100 meters, and in reflector less mode, whereas with reflector it's really huge, so it can go to almost 3 kilometers. So that difference in the range of the device is what we should take care. So what we should also keep in mind. So if we want large distances to be measured, then we should be able to also superimpose the readings of reflectors as well as non-reflectors. Hey, just a moment. Yeah, so what we saw over the ages that in reflector-less mode, people were trying to use some of the image-based features of the object space. So these features, it also needs some knowledge of digital image processing. So DIP concepts were used. So the robustness was increased. Robustness increased by the use of feature detection or feature extraction. Okay, so in in surveying, which is our domain, we used in image feature in image feature matching, and this was really challenging for the people who were working on image processing and uh, also advances in the application of computer vision. So some features like edge detectors, which we know, blob detectors, also line extractors, edge detectors like CANI, etc. are used normally. Also, people use some um, point features. Also, blob detectors. So all these types of detectors were used for the extraction of features. So is it clear, friends? Any discussion on the things that we are having now? Let me come to the class. Mm, Aditi, Aditi, are you there? No. Abhishek, Those who have understood, please raise your hands. Let me see. Those who have understood, please raise your hands. Saurabh. Oh, okay. Devashri, Shubham, Aman, Saurabh Chaudhary, Nanditi, Neeraja, Vinay, Santosh, Akash, Yash, Durga, Vikram, Nancy, Ashlesha, Dinesh. Uh, Dinesh, you could not take the exam or something like that? Was it you? Mid
No,
semester?
sir, it was another Dinesh, sir.
And another Dinesh. Okay. Huh. Ranjit, Uddar, Utkarsh, Ronak, Tanish, Rishav, Mohit, Abhishek. Okay. Okay. Yadav, Yash. Okay. So there are some interesting things. Yeah, you can down your hands. So thank you. So interesting things is in the sense that first there is some recommend of the image, and these images are not normal images, these are geospatial images. Okay, so there is a difference, minute difference between normal imaging and digital, normal digital images, DIPs, and geospatial images. Okay, so geo, and this along with geospatial data come up with formation of geoinformatics leading to geointelligence. Okay, so this is the chain, and maybe some of you might know that geoinformatics, geointelligence is one of the verticals in the research and development domain of even government of India, which was announced very recently within last 12 months or so. So if you have to, not only from the examination point of view, from the point of view of job, a lot of jobs are available for all of us, provided you increase the depth of your knowledge. So don't just get limited to small mining engineering domain, but you see a lot of extensions are possible. Extend your horizons. Also take interest to know the usages of DIP, even DSP. So the laser scanner, which our students built, that needed a knowledge for the signal processing, handling the microprocessors. So start working, and if some of you want, please come to lab. We have some of the latest microprocessors, and then if you have some ideas, we can definitely get that culminated into some task. Okay, so good. Coming to the computation of the length. Okay, so using this total station, what we are trying to say is we can measure vertical as well as horizontal angles, as well as in addition we can compute the horizontal distance, the slant distance, or the along the slope distance, and the vertical distances. So and if we know the bearing of any of the lines, we can get that mapped or correspondingly adjusted or propagated to all the other points and capture them with reference to the bearing of the given point. Okay, so all these are really easy. So let me see. Yeah. So if this is one of the scenario where we have to take the readings. So along this slope and this height, and this horizontal distance. So this height small d, this horizontal distance capital H, along the slope capital L. So all these can be measured by the use of electronic distance measuring devices. Okay, so all actually are converted so to a normal, trigonometry based computations, which is very simple. But then integrating that with the hardware devices, which call for, having a beam generator and then collecting them, getting a microprocessor, compute them is all necessary. So microprocessors are nowadays really taking the lead. Okay, so even some of the microprocessors, they are capable of capturing the image or video streamed data, as well as process them almost in real time, mode. Okay, so the microprocessor should be really powerful. Okay, and some of the adjustments like reducing the slope distances to horizontal distances, as well as taking the curvature of Earth into account. Taking the curvature of Earth into account, it becomes easy in current day. Sorry. Okay, so some of these distance conversions which are needed are getting clarified here. So you can see, is it visible, friends?
Yes,
Yes,
sir.
sir.
Okay, so if this is the instrument height and this is the reflector height, okay. So we normally have these heights at the same level. Okay, instrument height as well as the reflector height. Okay, and so the beam, this goes starts transmitted, getting transmitted from the instrument, and the reflector is here from the prism. It gets back. So we get the whole length covered. This angle that it maintains with the horizontal is alpha, and it should be the same angle maintained by the slope. Now you can see we can get the projected length, not the actual length, because there may be undulations. So you see the surface is not plane surface, so it's some portion is undulating, so going dipping in, some may be out, so protruding out also of the surface. Common line joining the base points of the instrument station with the observer station. So in this geometry, given the zenith and the alpha, we can also some measurements about finding L, we can get the D and H. So this is very simple as that. So so oh, yeah, elevation at A plus H of E, HE. This is elevation at A minus elevation at B plus HR. So HR, HE can be different, can be same. So normally it should be within the reflectance zone or incidence zone of the prism. So nowadays we have omnidirectional prism. So that's what is very new device that we have on the reflector side. So the difference in the elevation is used to reduce the slope distance to horizontal during field operations. Say HE is the elevation of the ED, and F or R is the elevation of the reflector above their respective station grounds at the mounting locations. And if the elevation station, if the elevations of stations A and B are say elevation A and elevation B, then the horizontal distance horizontal distance of the slope is capital H, and that gets computed once I find small d and capital H. So that is small d square root of small d square plus minus capital H square. So that is the basic trigonometry. And the difference in elevation between EDM, that is the small d, is this value. So we can easily compute them. So friends, let us try to solve this and get it done. All of you are able to see?
Yes, sir.
Yes, sir.
Okay, so please type your answer in the chat quickly. Okay, so Excel. Is anyone done with?
So could you show the question once again?
Then I need to unshare my Excel. Okay. Yeah. The blue part is the question. Is it viewable? Are you able to see, all of you?
Yes, sir.
Ah. So you need four data elements: elevation of A, HE, elevation of B, HR. Okay, so I can go to the Excel now. So I need to calculate small d, which is actually if this is elevation at A, this is HE, this is elevation at E, this is HR. So can you tell the values, anyone, quickly?
Sir, EA, sir, is it elevation of A?
Yeah, EA is
Sir,
elevation.
447.401.
Yes, 447 point
401.
401. Yeah, and
Sir,
HE.
1.417.
Yes, very good. And EB, elevation of B, someone else should tell, not you. I don't know who is telling.
Sir, it's 445.389.
Yeah, 4. And HR.
Sir, it's 1.615.
So D is actually equal to, okay, so D is actually this plus this. One point 814. Okay. If, if this is D, no, let me. So what is capital H? We have to find the capital H. The horizontal distance is the SURT square root of capital L minus square root of capital L minus this. L square actually. L square minus. Isn't it? Is it clear? So let me see. SQRT square root of. What is capital L, friends?
165.36.
Okay, so I can minus, and this is D is this into name. Let me see. So this is capital H. So this is actually your answer in meters. Is it clear? Any doubt? Let me see how many of you have written. Yeah, one Saurabh Raj has written yes. Saurabh Chaudhary. Let me see. It is the reverse image. 16.35040049. Yeah. Divya Sri. Yeah. Ashlisha. Good. Shubham Kumar. Yeah. Good. Okay. So. So what about the others? Amlipur. Amlipur is writing now. Good. The others are not writing. Why? Is it clear? Vikram?
Yes, sir, it's clear.
Okay. Nancy Mandal? Nancy, are you there? Nancy is not there. Okay. Partha
Yes,
Pratim?
sir. It's clear.
It's clear. Okay, okay.
Hello.
Hello, yeah. Okay, I got to hear you now. Okay, good, good. Very good. So, okay, some you are writing now. So, back little later. Again, so reducing the short lines to vertical angles. So, this is the same as if I know capital H, and I need to find L, or if I know L, I need to find capital H. So the trigonometric transformation H equal to L sine Z can be used. Okay, so this is basic trigonometric things. Now, as we were telling, errors in electronic distance measurements. Okay, so this is very, very important. So we also noted that accuracies are having two parts. Do you remember? So in our earlier discussions, we had.
So can you go to the previous slide?
Which slide? This one.
Sir, reduction in short line you have written.
Yeah.
Okay, sir.
Okay. So I can move from here to some other slide.
Yes, sir. Yes, sir. Thank you, sir.
So as we were telling, so in error or accuracy expressions, we earlier also saw that idiom we have two parts. So plus minus, some fixed component, and some ppm, parts per million, which is actually linearly varying with the variable observable that we measure. So 2 parts per million of the length. Okay, so the one is constant part and a scalar error proportional to the distance observed, whatever is the measurement that we are observing. Okay, so so once we specify the errors which vary for different instruments, but the constant portion is usually about the same, and the constant error is most significant for small distances. But for long distances, if we talk of an error of say 2 millimeter in 20 meters and 2 millimeter in 1 meter and 2 millimeters in 2 kilometers. So 2 millimeters error over long distances is actually negligible. It becomes actually marginal. Of course, the range of this instrument is to be taken into account, isn't it? So, which is why we have another, proportional part of the error, which is proportional to the observable. So, if the amount of the observable is more, the proportional part will be more. So, constant error for a measurement of 20 meters is good to only or 100 ppm. So 2 plus minus 2 millimeters. And for long kilometers, this is not that significant. Okay. So the major aspect that we need to concentrate is now focusing on handling the instrument, coming up with adjusting for the centering errors. So adjusting for atmospheric errors, adjusting for the ng, which we calculated in last 3-4 classes back. What was ng? Anyone who knows can write in the chat box. What was ng? No. Refractive index of group refractive. Yes, sort of. It should be group refractive. Divya is writing. So, and that NG calculation we saw is dependent on the atmosphere which is being, traversed, which is being traversed by the ray, by the signal. Okay. And okay, so then we have also some components which contribute to the error. Okay, something like plus minus 2 ppm constant error plus minus the proportional error if it is 2 ppm. So if the length is say 2 kilometers, how much is plus minus 2 ppm? Can anyone write? Plus minus 2 ppm of say 20 meters is how much? Quickly let me know. Plus minus.
So what is the question?
2 ppm, yeah, plus minus 2 ppm of 20 meters equal to what? Plus minus, I have written, so in the chat you answer quickly. One has written, and others? Saurav Raj. Okay, good. 0.04 mm. Okay, so 20 meter by 20 meters and 2 ppm of 20 meters. So into 2 by 10 to the power 6. Okay, so good. 104 mm. Okay. Okay, good. So the major error components in an observed distance are instrument and target miscentering errors and the specified constants and scalar error of the instrument. So constant is the constant part and scalar error is the fractional part. So if there are some errors in centering of the instrument and the target, so those errors will come plus the constant errors and the uh, fractional part. So if EI, okay, EI and ER. EI is the estimated miscentering error of the instrument, and ER is the estimated miscentering of the reflector. EC is the constant error of the EDM, and the ppm of the specified scalar part of the proportional part is ppm, and d is the measured distance, whatever slope or whatever we consider. Then the total error in the measurement will be d equal to square root of summation of squares of each of these. Is it clear? Any doubt? What is EI here? What is EI?
Miscentering error of instrument.
Yes, EI is miscentering error of the instrument. ER, that of the reflector. EC is the constant part, and the ppm into d, whatever is the distance, if it is total station getting used for finding the distance, and then we will have this squares and sum, then square root. Okay. Okay, so
Sir,
based
what
on
is EC?
what is EC? EC, yeah. What is EC? Anyone who can say? What is
Con-
EC?
Constant error.
Yeah. So we have the constant error. Constant error, as we showed. Yeah. Which is the constant error? Which is EC? What is the value of EC here? In this portion, what is the value of EC?
2 mm.
Yes, 2 mm. And this 2 ppm is the scalar proportional error. Okay, so is it clear, friends?
Yes, sir.
Yes, sir.
Okay, so with that, let us go and solve this problem. Please note down the blue parts numerical values. And type your answer in the chat quickly. Are you all solving it? Noted down the
Sir,
input.
the values are not given.
Sir, that diagram is with the.
No, that diagram is not needed.
Sir, but how we will know what are
Sir,
the
yes,
errors?
sir, it's written estimated error of the number is missing there.
Okay, yeah, so someone is reading it. Good. So it is the same, 2 mm plus minus 2 ppm, whatever we used earlier. Just a moment, let me cut paste. It should come here, isn't it?
Sir, but centering error, what is that?
Yes. So centering error is of the instrument plus minus 3 mm and target is plus minus 5 mm. Instrument centering error, say plus minus 3 mm, and the target was plus minus. So are the data now all available to all of us? Now, please write the answer in the chat box quickly. We have to calculate ED. We know we have EI, we have ER, and we have the ppm. Okay, so Ashlisha, are you there? Or who is helping me today?
It's me.
Divyasri. Divyasri, can you tell the values so that I key in on the Excel?
So it's either plus minus 5 mm or 3 mm. I'm confused between EI and ER.
EI, why confused? It's a square. Even if it is plus minus, you take the square. So EI square will be what we will be needing, isn't it? So we'll do EI square, we'll do ER square, all will be squared terms. So is it the confusion or something else? I don't know.
So no, sir, the value, the EI and ER, they are either 5 plus minus 5 mm or plus minus 3 mm. The both of them.
No, why? One moment.
So like the EC is 2 mm.
One moment. Let me get to the question. Okay. So EI is this one. Is the power point visible?
Yes, so now it's clear.
So yeah, that's fair. Okay, good. So now let me go to the Excel. So ER is EI. Okay, EI is 3 into 3. EI square, isn't it? ER.
It's 25.
EC.
It's 4.
And then the ppm. It is actually so it should be. Let me see. 2 into 10 raised to the power minus 6. And what's the distance?
It's
827.
827.329.
I should multiply it here. 8 to 3. Oh, 8 to what? 8 to 7.
827.329.
The square of that. Okay, so this is the component wise. So sum them and square root.
So that distance is in meter, rest are in millimeter.
Achha. So we have to convert it to multiply by 1000, isn't it? So yes. So then this should be multiplied by 10 to the power 3. So I can remove 3 decimals of it. 329. Okay, 329. 329, no? Is it clear?
Yes, sir.
Okay, 2 has gone. 292. Good, very good. So this is the plus minus. So you have to write plus minus of this as. Okay, so plus minus this much is the error in the computation. Is it clear, friends?
Yes, sir.
Okay, so good. So is there any doubt for whatever we discussed today? We can take up some doubts now before we stop for today's class. Anyone? Yashraj?
Yes, sir. No doubt.
Everything is clear?
Yes.
Okay. So, Divyasri, things are clear with you?
Yes, sir.
Okay, so we'll end the class now, and about what we need to do for hybrid, I also don't know, so we will update you on the MS team. Okay, so how many of you are in campus? All of you? And then how many are not in campus?
Sir, I am not in campus.
Okay, so three of you are not in. So quite a few. Okay, so what should we do? When are you supposed to be back?
Sir, 9. 4, sir.
Okay, maybe but then we can ask what is the who are in campus. We will ask in the MS team, and accordingly you please reply. And then those who are planning to come by 4th or 9th, so for them we can have another session. So good. We will accordingly go ahead, isn't it? So as of now, I can see that some. How many of you are there? 11 of you are not in. Okay, so maybe we will have some more queries in the MS team, and we will start the discussions on MS team. Okay, is it clear, friends?
Yes, sir.
Yes, sir.
Okay, so you can put your hands down, and then I can close the class now. Thank you.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Bye.